Alright, so today I'm gonna be explaining this important article on oversquashing in message passing neural networks, the impacts of width, depth, and topology. This is important paper in ICML 2023 by Michael Bronstein. So message passing neural networks are instances of graph neural networks that leverage the graph to send messages over edges. This inductive bias leads to a phenomenon known as oversquashing, where a node feature is insensitive to information contained at distant nodes. Despite recent methods introduced to mitigate this issue, an understanding of the causes for oversquashing and of possible solutions are lacking. In the theoretical work, we proved that neural network width can mitigate oversquashing, but at the cost of making the whole network more sensitive. Conversely, depth cannot help mitigate oversquashing. Increasing the number of layers leads to oversquashing being dominated by vanishing gradients. The graph topology plays the greatest role since oversquashing occurs between nodes at high commute time. So when the distance is too big, for example here there is some click, another click, and then bottleneck, some big graph. Then because of this bottleneck, the distance between this and this node is huge, and the commute time, hitting and then come back, the commute time is too long. So this links like this, these sparse things that connects two very dense subgraphs. These sparse nodes, very few, that we use in Mincut to get such communities. Because of these links and because the distance between two distant nodes makes the message passing, so you need at least k layers to send a message from one to another node, which is k hop away. And also this problem of vanishing gradients also is mixed with oversquashing. That's why the problem is very sophisticated. Of course, oversquashing is also mixed with underreaching phenomena, So because of this mixed phenomena, people confuse these things. But we should separate these concepts. They have their own concerns. We should have a separation of concerns as a principle in software development. So this aggregation and update here, this is a standard message passing. But since in an MPNN message passing neural network, the information is aggregated over neighbors, for a node V to be affected by features at distant R, so it needs at least R layers. So here you see, for example, the commute time between two distant nodes is high. And Chigurh constant, I have explained this in a different playlist, spectral graph theory. These Chigurh constants, these are very important things like effective resistance, commute time, hitting time, important things in random walks. So the impact of width. So we consider this class of message passing neural networks. And so we have this theorem for sensitivity that the change of variation of the derivative of the mth node with vth node with respect to u's node, for example, two nodes that are far away, v and u, if you just take derivative, so the upper bound is this. So we learn from this that the topology is play an important factor, and also model, but topology is the most. So if you want to reduce your oversquashing problem, you should care about the topology. How can you reduce those bottlenecks? So the Lipschitz regularity and width of underlying message passing can help mitigate the effect of overall squashing. However, it is a remedy that comes at the expense of generalization and does not address the real culprit behind oversquashing, the graph topology. So the impact of depth. So this theorem says that given a message passing, so we have two nodes V and U again. There are distance R away with shortest path distance. They have distance R. Then C sigma, this one. Let it be the Lipschitz constants of sigma. Omega, the maximal entry value over all weights matrices. And this D mean is just the minimal degree of G. Minimal degree of G. And this gamma is the number of walks. Number of random walks from V to U of maximal length L. So if the number of walks is too high, it means that it has a higher upper bound. And there exists CK independent of R and of graph. So to understand this formula, equation 4, we need to fix K, which is less than R. And R is here. We need to fix K and assume that nodes are badly connected, meaning that the number of walks of length at most R plus K is small. So there is not a good connectivity, let's say, between them. They suffer from a very good and redundant connectivity. So the bound on the Jacobian decays exponentially with distance R. So the band above considers D mean and gamma as a worst case scenario. So the theorem, this 4.1, implies that when the depth is comparable to the diameter of G, oversquashing becomes an issue. If the task depends on the interaction, I can say you're getting far away, loosely speaking, I can say that you're getting far away from a good expander, because an expander doesn't have these problems of oversquashing. At least the problem is very reduced. The oversquashing phenomena doesn't bother, so it is very small. But if your graph is too far from an expander, then you have a very high reaching to distant nodes, very poor connectivity, lots of bottlenecks. So that is the story behind this idea of oversquashing. But then is it another couple, vanishing gradient is also coupled with the concept of oversquashing. So we should take care of that to decouple these ideas. How can we do that? We just write the derivative with respect to the parameters, and the sensitivity, the vanishing gradient will come out. This will provide exact conditions to incur the vanishing gradient, instead as the gradients of the loss decaying exponential with number of layers. So this is important. This can be upper bounded by this. So given any weight theta entering a layer K, there exists a constant independent of M. And the gradients of the loss decay to zero exponentially fast. The problem of vanishing gradients for graph convolutional networks have been studied from an empirical perspective. And this theorem provides sufficient conditions for the vanishing of gradients to occur in a large class of message passing neural network that also include residual connection through the contribution of C sub r. This extends the behavior studied for recurrent neural networks to the message passing neural network class. So this bound in 4.2 seems to hide the contribution of the graph. This is in fact because the spectral norm of the graph operator S V is that one, and we reserve the investigation of more general graph shift operators. So as I said, the impact of topology is very important. So you need to know about access and commute time, because when you want to integrate information across different layers, for example, here we introduce this quantity, J. We provide an intuition for this term. We say that node V at layer M is mostly insensitive to information sent from U at layer K. Then, on average, we expect this to be much less than the gradient of HM over with respect to HV. So node V, U, V, V. If you look at this, you understand that it is changing. It is seeing the sensitivity of the HV with respect to HU, and at layer M, and the other one is at layer K. So there are cross layers. Do you see that there are cross layer? For example, here if you are at layer M, here if you are at layer K, and we want to see the sensitivity between them. And if we just do it with respect to V itself, so V itself goes to the next layer, but this is the just between two nodes, but this goes across layers. So in the opposite case, so this J will be larger when V is roughly independent of information contained at U at layer K. So the Jacobian obstruction of node V with respect to node U after M layers is this sum. So if V is the smallest singular value across all weight matrices, then we have this lower bound. Because larger O means that after M layers, the representation of node V is more likely to be insensitive to information contained in U, and conversely, a small O means that nodes V is on average able to receive information from U. And finally, they talk about the relationship between oversquashing and commute time. So they make it symmetric, and so we have this symmetric quantity. The symmetric Jacobian obstruction is defined by this variable, symmetric Jacobian obstruction. Again, look at these. We are at layer M, and then we are here at layer K, node V, node U, V. And then, so there is an upper bound and lower bound. So we are, let's say, sandwiching this important variable O, this symmetric Jacobian. We are sandwiching it between an upper bound and lower bound. And look, both of these lower and upper bound is just dependent. It means that we only need to know the commute time, tau. That's why tau is a critical concept, variable, that we need to investigate and numerically approximate it. So what did we do? We investigated the role played by width, depth, and topology in oversquashing. We have proved that while width can partly mitigate this problem, depth is instead generally bound to fail, since oversquashing spills into vanishing gradients for a large number of layers. So we have shown that the graph topology plays the biggest role, with the commute access time providing a strong indicator for whether oversquashing is likely to happen independently of the number of layers. As a consequence of our analysis, we can draw a unified framework where we can rigorously justify why our recently proposed rewiring methods do all alleviate oversquashed. But there are limitations. The analysis applied to message passing that weigh each edge contribution the same up to a degree normalization. It's not a big limitation,